Welcome to Aero Engineering 210 Lesson 7. These are the lesson outcomes for this lesson. Please hit escape and take a moment to review these outcomes. And then when you're ready to resume, just hit the slideshow button again. In this lesson, we will continue to learn about fluid dynamics by applying the continuity in Bernoulli's equation that we learned in the last lesson to understanding how lift is produced and how we measure airspeed. We begin by recalling that the continuity equation and Bernoulli's equation were derived from two laws of physics: conservation of mass and conservation of momentum. Continuity was derived from conservation of mass, and Bernoulli's equation is a statement of and was derived from the conservation of momentum. Reviewing the continuity equation, we note that the important assumptions are steady flow and one-dimensional flow, and really flow perpendicular to the plane in which the flow direction is measured. And that when we do that, we can state that the density times the area times the velocity of flow into a stream tube or a wind tunnel or anything like that is equal to the density times the area of the exit from that tube and times the velocity out of that tube. And that's our continuity equation. We take one more step to get Bernoulli's equation. We want to integrate that thing along the streamline from station 1 to station 2. Now, this would be a rather messy integral if rho was a variable, but if we assume incompressible flow so that rho is a constant, and we can take rho outside the integral, then it becomes easy to integrate. We integrate that equation on both sides from station 1 to station 2, and we get an expression that says that the change in pressure on the left side of the equation is equal to the change in 1/2 rho v squared at station 1 and station 2. Write that down below. That's what we call Bernoulli's equation. P1 plus 1/2 rho v1 squared is equal to P2 plus 1/2 rho v2 squared. And there's the assumptions again summarized on the right. Now, this is true anywhere along the streamline, so that the sum of the two pressures there, because they have units of pressure, is a constant anywhere along the streamline, and we're going to give that a name. We're going to give all the terms a name. In fact, the pressure is we're going to call static pressure. 1/2 rho v squared we're going to call dynamic pressure, and the total of those two, which is a constant anywhere along the streamline, we're going to call total pressure. Likewise, you recall that Bernoulli's equation relates static pressure to velocity by stating that the total of static pressure and dynamic pressure, with dynamic pressure being 1/2 times the density times the velocity squared, is equal to a constant we call total pressure anywhere along the streamline. With using Bernoulli's equation, we can relate the static pressure at one point on a streamline to another point by knowing the velocity difference, or vice versa. By knowing the pressure difference, we can determine what the velocity difference is. And recall that this equation assumes steady, inviscid, incompressible flow along a streamline with negligible body forces. This behaves a little bit like a pendulum in that if you think about static pressure as the potential energy and dynamic pressure as the kinetic energy, then they can change from one form to the other. As the velocity increases, the pressure goes down, and as the pressure increases, the velocity goes down. And that's what Bernoulli's equation tells us. So now let's apply this to flow past an airfoil. If you'll notice, the streamlines on the upper side of the airfoil are squeezed together by the shape and orientation of the airfoil. The streamlines on the bottom are not, so that there is a velocity difference between the top and the bottom, and this produces a pressure difference between the top and the bottom, and this in turn produces lift. You may have been told that the reason the flow goes faster over the top than over the bottom is because it has farther to go to get to the trailing edge, and that those two flows must meet at the trailing edge. There's a great movie for today in the viewing list that proves that this is not true. They use pulse smoke and show that in fact the acceleration of the flow over the top of an airfoil at angle of attack is much greater than that required to have the flow meet at the trailing edge. In fact, it is due to the restriction to the airflow, just like putting your thumb over the end of a garden hose, caused by the shape and orientation of the airfoil. We can also use these same equations to measure airspeed. We can take a tube and put it out into the stream aligned with the airflow, and stop up the rear end of that tube or connect it to one side of a manometer so that the air in the tube is still. And then the opening of the tube, which is perpendicular to the airflow, will be a stagnation point. The air can't flow in because there's already air in the tube. So the flow comes to a stop, and the pressure, the static pressure, increases to equal the total pressure along that streamline. Then we can put static ports elsewhere, maybe on different sides of a pedostatic tube as shown here, or other places on the aircraft where we think the velocity is going to be approximately equal to the free stream velocity. And we can measure static pressure with those ports because they're parallel to rather than perpendicular to the airflow, and hopefully the velocity is approximately equal to free stream velocity. If we connect the static ports to the other side of the manometer, then the difference in the heights of the columns in the manometer is proportional to the dynamic pressure, and that we know is proportional to the velocity squared. And that's one way to measure velocity of an aircraft. More commonly, instead of using a manometer, we hook up those ports to a pressure gauge, a differential pressure gauge, and we calibrate it in airspeed. So we know that the pressure changes with velocity squared, the difference between those two, which would be dynamic pressure. Look again at the Bernoulli's equation to satisfy yourself that the difference between total pressure and static pressure is the dynamic pressure. That's proportional to velocity squared, and all we have to do is change the gearing mechanism in the gauge and the calibration of the dial so that it reads in velocity rather than pressure. But there are some corrections we have to make and some definitions we have to make. For instance, if we're not flying at sea level, then the density is not right, and so dynamic pressure has to be adjusted to give us the true airspeed. And likewise, there might be other reasons that we have to make corrections to the airspeed we read on the airspeed indicator. We call that indicated airspeed. It's what we read. And the first thing we have to correct it for is the fact that perhaps those static pressure ports are not located in a place where they can measure free stream static pressure. Perhaps the pressure is modified slightly by the speeding up of the flow as it goes around the airplane or around the pedostatic tube. And there might be other errors like machining and installation errors. There might be some dynamics of the actual pedostatic system, the tubing that runs from the ports to the indicator. We correct all those with something called position error, which is determined from flight test. we add the position error to the indicated airspeed to get calibrated airspeed. Then we multiply by a compressibility correction factor. We use the symbol F to get equivalent airspeed. We determine the value of F factor that we should use from a table like the one on page 568 of your textbook, or the one shown here in the slideshow. Notice that at low speeds and low altitudes, the airspeed, the correction, the F factor is very nearly 1, and the correction is very small. But at high altitudes and high air speeds, where the Mach number is much higher, we see that the correction is much more significant. The value of F is a lot smaller and the correction is not at all trivial. And that's why we call it a compressibility correction, because it's more significant when the flow is more compressible. It's worth noting that equivalent airspeed is that airspeed that would give us the same dynamic pressure at sea level that we are actually measuring with our airspeed indicating system. And that's why it's called equivalent airspeed, because it's the airspeed that would give an equal value of dynamic pressure at sea level. So once we know equivalent airspeed, in order to get true airspeed, we have to multiply by the square root of the density ratio. And if you remember that true airspeed is always higher than equivalent airspeed, you can easily remember that in that radical sign, the density has to go on top. The sea level density has to go on top, because it'll always be greater than the density at higher altitudes in the standard atmosphere. Once we have our true airspeed, we're not done, because what we really want to know is how fast we're going to get where we're going. And to determine that, we have to correct our true airspeed for the wind to get ground speed. Our true airspeed is our speed through the air mass, but on a windy day the air mass is moving quite rapidly relative to the ground. It might either help us or hurt us. So in order to determine what our actual ground speed is, we have to make a vector addition of our true airspeed and the wind velocity. And that'll tell us how fast we're going to get where we're going. So here's a summary of ICeT. There's a couple of ways we have of remembering it. This radical sign is like a graph of indicated, calibrated, equivalent, true, and ground speed. We have the bar level between indicated and calibrated because position error is usually quite small. And we have the bar level between true and ground speed because we don't know if the wind's a headwind or a tailwind. And for high-speed aircraft, the wind velocity is relatively small compared to the speed of the aircraft. The most important thing about this radical sign, though, is to remind us that equivalent airspeed should be the smallest of all the airspeeds unless we're flying at sea level. And so that's a good sanity check when you do your GFASICS methodology to go through and do a airspeed problem. You can sanity check that equivalent airspeed should be the smallest speed of all of them. The way that we write ICeT to remember the relative magnitudes of the different velocities is we'll write a uppercase I and C, then a lowercase e, and then a larger font uppercase T as shown in the upper left hand corner of the slide. Also notice on this slide that the abbreviations, actually acronyms, KIAS, KCAS, KEAS, and KTAS are shown and defined on this slide. These are commonly used in aviation. KIAS is knots indicated airspeed, KCAS knots calibrated airspeed, KEAS, knots equivalent airspeed, and KTAS, knots true airspeed. And even countries that use the metric system SI often use knots as the units of airspeed. So it's a very commonly used measure of velocity, nautical miles per hour, and abbreviated knots. And it's and these acronyms are also commonly used.